Hi class, this is Mr. Krieger. I'm also teaching this class on behalf of Mrs. Stillman's classes and Mrs. Berthel's classes. This is lesson 2 in Unit 8, Part 2, Proving Triangles Are Similar. So make sure you print up a copy of the lesson, please. All right, so first thing we're going to do, we learned how to prove triangles similar using angle-angle similarity, side-angle-side similarity, and side-side-side similarity. We're primarily going to be using, almost exclusively, angle-angle similarity in the actual proofs. But we're also going to be going further than proving triangles similar. If you remember, corresponding parts of congruent triangles are congruent. Remember that? CPCTC? Well, that can't work in similar triangles because in similar triangles, corresponding sides would not be congruent. But there's something similar or something analogous for similar triangles, and that is if two triangles are similar, then corresponding sides are in proportion. Okay? And we know that. We know that, for example, if these triangles are similar by side-side-side similarity, but we know that this side compared to this side and this side compared to this side have the same ratios. I'll show you a little more detail. This is the smallest side of the little triangle. This is the smallest side of the bigger triangle. This is the medium side of the small triangle. This is the medium side of the larger triangle. And if we actually make that proportion with numbers, 6 is to 9 as 8 is to 12. That reduces to 2/3. That reduces to 2/3. It's true. Now, in our proofs, we're not going to be using numbers. We're just going to be using the names of the sides. So this is what it will look like in the proof. AB is to DE as BC is to EF. Those are the matching sides, and that's what you're going to see in a proof, this kind of proportion. So let's actually try to do a proof like that. Okay, in fact, this is bleeding through. I'm going to put this underneath. All right, so here's our first example. We want to prove that this little triangle here is similar to the big triangle. In other words, triangle ABC is similar to triangle DBE. Okay? Plus, we also want to prove this proportion. Well, that makes sense. If triangles are similar, then the corresponding sides are in proportion. Let's actually check to see if those sides correspond. BD is this piece, corresponds to BA. Remember, the left side for the little triangle corresponds to the left side for the big triangle. As BE, the right side of the little triangle, is to BC, the right side of the big triangle. So all we need to do is prove that the triangles are similar, and then we could use what we just learned here. If two triangles are similar, then corresponding sides are in proportion to justify this part B, why that's true. Okay, so again, I like to do my proofs with bullets. You want to put down your given. DE is parallel to AC, and we know that's given. Now, what does that give us? Well, parallel lines, we have parallel lines here. We can consider that line like a transversal. So when two parallel lines are cut by a transversal, what kind of angles are congruent? Corresponding angles are congruent. So we're going to say angle BDE is congruent to angle A. By the way, we only have to name A with one letter because there's no confusion. There's only one angle by A. But by D, there's an angle up here by BDE, and there's also an angle below ADE. So if you want to name an angle where there's a confusion about which angle you're talking about, you should name it with 3 letters. All right, so we know those angles are congruent, and I'm going to give you the official reason right now. If two parallel lines are cut by a transversal, then corresponding angles are congruent. Remember, we're trying to prove that there are two angles in the big triangle that are congruent to two angles in the little triangle to use angle-angle similarity. That already gives us one angle. Now, we could even use this side as a transversal and get those two angles, but I want to also show you an alternative. Angle B, put a little X on it, angle B is in the little triangle and in the big triangle. So we could say angle B is congruent to angle B, and you know the reason. It's the reflexive property. Okay? Now we have enough information to prove that the triangles are similar. Triangle ABC is similar to triangle DBE because what we learned in the last video, last lesson, angle-angle similarity. And now the next thing is going to be like CPCTC, but not for congruent triangles. For similar triangles, we know that in similar triangles, the corresponding sides are in proportion, and that's exactly what we're going to write. We say because if two triangles are similar, then their corresponding sides are in proportion. Okay? That's that proof. So we'll try, before we do another proof actually, want to show you something else. Here is a proportion. Now, you know, if you ever have a proportion that you want to solve, I'll give you an example. Suppose we want to solve the following. I'll put it over here. Suppose we want to solve 3 over 10 equals 6 over x. You know you've got to cross multiply, right? Well, what about in this case? Same thing. It's a proportion. If we wanted to solve it, we're allowed to cross multiply it, right? So that's something that we're going to take a look at now. But before we do that, I want to take another way to look at a proportion. Maybe in elementary school, you learned a proportion can be written as an equality of two fractions, or you could have learned that it was a ratio A to B and C to D. This is another way of writing a proportion. Now, this first and this last part are called extremes. And this part and this part are called means. And there's a good reason for that. Means are middle numbers. Mean literally meaning, when you think about an average is a middle number. These are the two numbers in the middle. They're called the means. The numbers on the outside are called extremes because they're furthest away from each other. So if you want to tell which are the means and extremes when you have two fractions as opposed to the proportion being written out this way, this is the very first item and this is the very last item, and those are the two middle items. So the first and last parts are called extremes, and the second and the third, the middle parts, are called means. Okay? And here's another fact that we're going to use in our proofs, and it's a fact that you should just know. In a proportion, the product of the means equals the product of the extremes. Basically, it's saying you can cross multiply, but this is the official way of making that statement. When we've used the terminology cross multiply, that was just us talking in a simple language, but the correct mathematical language is the product of the means equals the product of the extremes. So if you were going to do the cross multiplication here, the way it's going to look is AB and EC are the extremes, so I'm going to multiply those. AB times EC, that's a product, and that equals to the product of the means. It doesn't really matter if you do means first or extremes first. The thing is, the extremes get multiplied together and the means get multiplied together. Okay? So the reason for this is the product of the means equals the product of the extremes, and we're going to now see that in a proof. So let's go take a look now at the next proof, question 3. You're given that these lines are parallel, SU and Y and BY. We want to prove that the triangles are similar. We want to prove that the corresponding sides are in proportion. And then we want to prove this. Well, this looks similar to what we just did. The product of the means equals the product of the exchange.